Hello, my name is Russell Irvine, and this is the final presentation for EEO 441 Engineering Design, Spring 2016. In this presentation, I will cover the digital multimeter that I designed and built with the assistance of Professor Guzman. The stated design goals of this particular project were to create a digital multimeter based off of a small commercially available microcontroller, Arduino in this case, with the stated goals of small form factor, low power consumption, some type of automatic turn off capability, with the stated features of DC voltage measurement from 0 to 10 volts, DC current measurement 0 to 100 milliamps, and the large range of resistance measurement from 0 to 100 kilo ohms. The design itself ended up being built off of the following components that you see here. These items, at the heart of which is the Arduino Pro Mini 328, which uses an ATmel 328 microcontroller. After a lot of assessment of commercially available microcontrollers, I settled on the Arduino Pro Mini for two main reasons. One, it had the minimum required functionality, namely 4 analog to digital converters, or ADCs, and it also had enough digital I/O ports to control the unit and also output the signal for the LCD display. The one issue that I did have with the Pro Mini was that it did not have a USB interface. And the second item that we can see here on the screen is the SparkFun FTI Basic Breakout, which just takes a USB port and converts it to the proper communication standard that works with the Pro Mini. The next item that we see here is the LCD screen, which I ended up choosing. A very standard approach for this particular type of program or small microcontroller design would be a 16 by 2 character LCD screen. But for this particular design, I ended up determining that all the results that I needed to display could fit on an 18 by 2 LCD, which allowed for a smaller form factor and for a lower current draw. Both the Pro Mini and the LCD I found work off of a 3.3 voltage. This has been kind of a newer development in that usually these smaller microcontrollers would run off of 5 volts, namely being powered off of a USB type of port. But for this particular design, I chose to go with the 3.3 volts because it allowed for the use of also commercially available lithium batteries. The average voltage of these type of batteries is approximately 3.7 volts, and with a 1000 milliamp hour rating, it would supply more than enough current for this particular application. And once I chose the battery, I also was able to find a commercially available USB charger which would power the battery, which made the overall unit possible to be recharged via any USB port, in the hopes that the unit could just be plugged into any computer or wall outlet as necessary to charge up the battery for further use. This is the overall design schematic for the entire unit. The schematic itself was generated using OrCAD software and shows all of the individual blocks of the design that ended up going in together. I will go into further detail regarding all the different aspects of this, but to see the entire unit laid out as one entire schematic, I felt was necessary just to make sure that everything was connected up properly and we could move forward as necessary. The next software that I took advantage of is a program called SolidWorks, which uses computer-aided design to build a 3D representation of all the pieces and parts of the unit and fit them all together. You can see that a fair amount of detail is presented in these pictures here, to include the battery, the microcontroller, the LCD, the switches, and the Pomona banana jacks where the unit would be plugged in. The only real modification that had to be made to the case itself was just a few holes, which were also able to be directly designed into the model. With these items, both the schematic and the solid model, I began to work on the layout of the overall unit. In the schematic, you can see the manufactured schematic for the microcontroller and the associated board. The board itself contains very minimal circuitry. It's just the microcontroller and a voltage regulator, and the crystal, which actually drives the unit. I did not end up using the onboard reset switch. Didn't really suit my purposes, but what you can see in the picture on the right is how the microcontroller Pro Mini Arduino board and the FTDI basic breakout were married together. Next up, we have some of the major capabilities for power. Originally, my intent was to use some type of watchdog timer in the in software that would keep the unit activated for a given amount of time before it would go into some type of turn off mode. But I found that due to the lack of I/O ports, and the microcontroller did not actually contain enough capability internally to put it into a low power state, I found that simply just removing power from the unit completely was the best path to move forward. This was accomplished with an MIC 155 monostable one-shot, which you can see in the timing circuit schematic in the left corner, that is activated by a momentary switch which applies a ground pulse to a trigger. That pulse is then holds the output of that unit in a high state based off of a small capacitor and resistor, which set up a timing constant. This is then used to hold a power MOSFET, which has both an N and P type MOSFET transistor, which acts effectively like a solid state relay. When the trigger is activated, it puts the power MOSFET into a power mode, which then supplies the 3.7 volts from the battery directly to the rest of the circuitry. One of the main issues that I had with this particular circuit was finding that when the initial pulse was given, it would meet the effective time constant that I was expecting, but then subsequent triggerings of the circuit would greatly lessen the amount of time that the unit was being held on. I found that what was happening is the main capacitor in the time constant circuit was not fully discharging, which meant that as soon as it would reach its given voltage, where it would just kept turning itself off again. The way that this problem was addressed and ultimately resolved was the momentary switch out front was changed to a dual pole, which provided a second path by which the capacitor itself could be grounded out across a 10 ohm resistor. So at the same time that it gets the momentary ground or low going pulse to turn the unit on, it also provides a temporary path to ground for the capacitor, which discharges it, and gave very consistent results. The final product, every time that the momentary switch is depressed, provides approximately an 8.5-minute unit power on, which I have found is more than adequate to make simple measurements and turns itself off, so it works as advertised. On the right side, you can see the manufacturer supplied USB charging circuit, which is nothing more than just a commercial off-the-shelf chip, which takes in the USB voltage and provides the required power to the battery for charging. The board itself was modified. The small connector was removed from both the battery and from the charging circuit, and wires were just laid down just so that I could combine both the battery, all the time circuitry, and the power MOSFET onto one, effectively a blade, which we can see here in the bottom is the actual implementation. Although it's not very pretty, you can see that the main capacitor in the right corner, upper right corner of the blade, is attached using a electrical grade hot glue, along with the board itself and the other components. The actual timing circuit and power MOSFET themselves were supplied are a surface mount type of technology, which are very small, and in order to properly connect up to these, it's commercially available to find small little breakout boards or daughter boards that you can see glued to the overall blade assembly. The next aspect of the build was for the voltage and current implementation. All four of the ADCs work in such a manner that they have a 10-bit accuracy across the given voltage range of the chip itself, which is approximately 0 to 3.3 volts DC. And then the ADC will break that down. 10 bits equates to 1024 individual steps across that particular range. So for the voltage measurement, the only thing that really needed to be done was just to create a voltage divider, which would proportionally divide up the 0 to 10 volts DC down to a 0 to 3.3 volts DC. The circuit that you can see built here was set up to provide approximately 10,000 ohms of resistance across the voltage that was being measured to minimize the amount of current. And it was also designed with a 0 to 500 ohm potentiometer, which allowed for proper adjustment and refinement when testing and implementation was finally completed. The finalized circuit can be seen on the left side of the implementation blade. You can see the resistors, the potentiometer, the wires. Again, it's not very pretty, but the hot glue is very effective in holding everything in place. Due to the small gauge of the wires that were being used, it seemed the best way to hold everything together so that things would not break. On the right side, we can see the current monitor circuitry, which is based off of the premise that 0 to 100 milliamps DC put across a 0.33 ohm shunt resistor will create a given amount of voltage proportional to what current is being supplied. In order to take that resistance and convert it over into a voltage, an INA 214 operational amplifier was used, which is specifically designed to work with current shunts for current monitoring purposes. This particular operational amplifier has a gain of 100, which When you work out the math, the output of this will be 0 to 3.3 volts, depending off what is being created across the shunt resistor. The other reason for using this type of circuitry is that it creates effectively an infinite input impedance, which is being put in parallel with the shunt resistor so as not to affect the overall current being generated. In the schematic itself, you can see that there is a 0.1 microfarad capacitor on the other side the ground to voltage pins of that particular chip, which is the manufacturer's suggested way in which that the unit be hooked up to avoid any type of oscillation. The actual implementation of this particular circuit can also be seen in the picture below on the right side. Again, the chip is a surface mount component, so the required daughter board was also used to build the circuit, and the large resistor that is coming off of what looks like the fourth pin of the small board is the large shunt resistor. The reason for such a large size of resistor was just due to its rating for its power consumption. It was many factors larger than it needed to be, but I figured that it would be better to err on the side of caution to make sure that there was no issues with all of the required circuitry being held down again by the hot glue. Next came the ability for the resistance measurement. The range of 0 to 100 kilo ohms, when compared to the actual resolution of the ADCs, was effectively too large. So in order to make it a more manageable measurement and more accurate, the resistance measurement was broken down into two separate aspects. A high resistance measurement of 1 kilo ohm to 1,000 kilo ohm range, and then a low resistance measurement circuit of 0 or 1 ohms to 1,000 ohms. The reason for this, using the 10-bit accuracy of the ADCs, this made it a much more manageable circuit. The way that this measurement was created was to use an LM334 current source, which is a very simple 3-pin configuration, which uses a R set, a resistor, to set the amount of current output across a given load. So in the schematic to the left, for the high resistance current, you can see that a resistor of 3.4 kilo ohms was used, which would then provide or output through the terminals of the unit across a resistor under test, and a proportional voltage would be generated and then measured by the LT1797 operational amplifier. The same basic configuration is also used for the low resistance measurement, with the only difference being the actual size of the resistor to set the current. And then also there is a slight difference in the two resistors, or in one of the resistors used to make the operational amplifier provide a gain of approximately 1.5. Originally, this circuit was designed to use the operational amplifier like a rail-to-rail buffer of effectively unity gain. But it was found during testing that I had overlooked the actual capabilities of the op amp, let me rephrase. I found that the issue was that the current source was meant to always have approximately 1 volt of difference between the voltage high and the voltage low. Seeing as that the unit itself doesn't have a ground pin, the output of the current source had to remain less than a volt difference than the actual input voltage coming into it, which was, again, going back to the earlier circuit of approximately 3.7 volts. This meant that the chip itself, or that the current source itself, would only work up from 0 to approximately 2 volts voltage being generated across the resistor under test, which then required the operational amplifier gain in order to get the required 0 to 3.3 voltage output. This was implemented with both the high and low resistance measurements, and the final product can be seen below in another small blade that was created, again using the daughter boards to hold the surface mount component along with the required resistors to set up the voltage gain. The actual R resistors which set the current are mounted on the back side of the card, along with all of the required circuitry and wiring. Next up came the implementation of the monitor itself, which was a direct connection between the LCD and the microcontroller. You can see that 6 lines of the digital I/O are configured in software to communicate to the LCD along with the required power, and a 750 ohm resistor is installed off of pin number 3, which sets the brightness. This particular LCD has the capability of using a built-in LED to backlight the screen, but it was found that there was no need to use that LCD because the measurement was clearly visible once the 750 ohm resistor was installed. And so on the left you can see the schematic, and on the right you can see the actual implementation. One of the aspects of this particular project that really made the whole thing work was using a rotary switch, which is a 3-pole, 4-position switch. The reason for this is that all 4 of the measurement functions required a different configuration for the way that what circuitry the terminals would be connected to. And in order to not connect them all together, the switch was implemented. In the diagram to the left, you can see that the red terminal switches between 4 separate functions, which correlates with the 4 functions of voltage, current, high, and low resistance, as does the black terminal, which also switches before the required inputs for those 4 functions circuitry. The third aspect of the switch connects a ground signal to one of 4 pins, which connects directly to the input of one of the digital I/O ports. These 4 pins effectively act like an enable by providing a ground signal to one of 4 pins, which will then correlate in software to the required function that the system would be used. This was implemented in software by basically creating a digital word where the 0 would correlate with the particular function. This can be seen in the implementation of the software, which we have here. Although this is very difficult to read, this is all the software that was required to be written for the Arduino to function properly. Starting at the left, I'm not going to go all the way through this, but you can see the declarations of the I/O pins, or the actual ADCs, and which particular function they would be associated with. The selection definition, like I was just discussing with the rotary pin, you can see starting off here, you can see that the 0 propagates from right to left in the first four positions, 0, 1, 2, 3, and 4, which correlate to the voltage select, current select. Moving further on, it also declares which pins are going to receive that signal. And then we started setting up some of the smoothing functions which were implemented in the code. One of the more difficult aspects of this particular project was setting up all of this software and making it supply a readable signal. If just left without any type of smoothing, the display would toggle between values at a rate that the human eye just can't keep up. So a smoothing function was set up to, one, effectively average out readings so that the unit itself would supply a consistent reading without constantly having a bouncing bit at the end. And then also the display of that particular averaged reading was set up to output approximately one visible change every quarter of a second. Moving into the main aspect of the software, it's set up using what's called a switch case, where you provide the different cases, which are the particular functions of the voltage, the current, the high resistance, and the low resistance, which is kind of in two parts here. And then a default function, which, if going back to the beginning, if there were no zero being applied to the circuitry, it would default to just a statement, which is presented as you can see here, just digital meter. The reason this was digital meter is it was found that the only time a zero is not being presented to the unit is when it's first turned on. So I could have added any text into there, but I chose digital meter because that's just what it says. When you turn the unit on, it will display digital meter for a given amount of time, which is partially based off of the delay and also partially based off of the smoothing function that is built in, which we see implemented in this lower section, which increments through both the smoothing and the averaging. One aspect that I feel necessary to mention is this code right here is by far was the most time-consuming and hardest part of this particular project. I myself have been working in the field of electronics for close to 15 years now, with that almost all being in the hardware realm. So working in the software realm was a very time-consuming task. Luckily, one of the largest resources that I had was Arduino itself. The company provides a website with reference and tutorials on how to implement their code, very open sourced, very easy to read, and very user friendly, which allowed, after countless revisions, the final code to work as expected. Next up came putting the whole unit together. Similar to what we saw in the solid modeling, the case was selected, the holes were drilled, all the components were installed, and then the circuitry was built up on those blades. Starting off on the right side, we can see the master switch, the voltage and current circuitry, the resistance measurement circuitry. And these were small little L brackets were used to hold the LCD in place, along with the battery, the charging circuit, and the timing circuitry, which is underneath. And then off to the left, we can see the momentary switch, the dual pole momentary switch, and the terminals. But I also had to add in some marking onto the case itself, which can be seen on the right side of it, just telling all the functionality and keeping everything straight for the user. And that was able to once it was all said and done, and then I moved into the ability to test the capabilities of the meter. The meter itself ended up achieving an accuracy of approximately 0.2% of full-scale reading for all 4 functions. There was slight deviations in some of the readings off on the very upper or lower ends of the range, and this was just based on certain no circuitry is ideal, and but overall the readings were very accurate and as good as I could have hoped via the testing. One of the aspects that I implemented during the testing was the use of the programming port, which allowed me to effectively measure the readings of the unit and compare those to the readings off of a laboratory standard digital multimeter, which is I used a Keithley 2002 multimeter, which is exponentially more accurate than my meter itself, and I was able to use this meter as a transfer standard to get the readings that I wanted. And once I got those readings, you can see it here going back to the code that there is a small value for scaling the reading, which I was able to set up a scale factor, which allowed me to provide a more accurate display. And then finally, here's just, I am lucky enough to have a full laboratory at my disposal. I spent the last 15 years working for Lockheed Martin in multiple different realms, but I'm also head of production, which allows me to have all of the equipment and lab space that I could require to build my meter. So on the left, you can see a picture of the bench that I used with some of the equipment, cleaning products and soldering irons and all the different tooling that could be used to build up this project. And then on the right, you can see one of the early functional tests of one of the blades. You can see the lab equipment that I was using to set up for this particular test. It would have been the current testing. And if you look closely at the picture, you can see the actual Arduino and microcontroller and LCD are built onto one card, with the selection pins and ADC pins broken out, and then so all it required was using a clip lead to implement the switching that I wanted and then input a particular voltage. And here we again, like I said, this is the current that is being measured in just in a lab environment. This allowed for easy changes if necessary, and just overall implementation and build up of the card. And in finale, what I have here is a list of 4 YouTube videos, which I will also post, which show each functionality of the circuit being implemented. Each video is approximately 2 to 3 minutes long, which shows the unit being switched between the different functions and then hooked up to the appropriate test measurement equipment to provide the signal required. So in finale, that is my final presentation, and overall I was very happy that everything worked as it was scheduled to, and look forward to hearing your comments. Thank you very much.